Good day everyone, this is Christine Araneta, and for today, I'll be discussing Chapter 6. This report includes the following topics. First, reversible reactions and chemical equilibria, and second, thermodynamics and equilibrium chemistry. First, let's have reversible reactions and chemical equilibria. The idea that reactions are reversible is formulated by the chemist Claude Berthollet in 1978. A little trivia: in 1978, the chemist Claude Berthollet accompanied a French military expedition to Egypt. While visiting the Natron Lakes, a series of saltwater lakes carved from limestone, Berthollet made an observation that contributed to an important discovery. He knew that a reaction between Na2CO3 and CaCl2 goes to completion forming NaCl and a precipitate of CaCO3 as products. As you can see, we have here Na2CO3 plus CaCl2 yields 2NaCl plus CaCO3. Berthollet expected that large quantities of NaCl and Na2CO3 could not coexist in the presence of CaCO3. Since the reaction goes to completion, adding a large quantity of CaCl2 to a solution of Na2CO3 should produce NaCl and CaCO3, leaving behind no unreacted Na2CO3. This result is what he observed in the laboratory. The evidence from Natron Lake is the run counter to Berthollet's expectation. Berthollet's important insight was recognizing that the chemistry in the Natron Lake is the reverse of what occurs in laboratory. So the reverse of the given reaction is CaCO3 plus 2NaCl yields Na2CO3 plus CaCl2. Based on the insight of Berthollet that reaction is reversible and that the relative amount of reactants and products determine the direction in which the reaction occurs, we recognize the ability of the reaction to move in both directions by using a double arrow when writing the reaction. So, we have here the Na2CO3 plus CaCl2, the double arrow which indicates that the reaction is reversible, 2NaCl plus CaCO3. So we have here examples. First, for salt hydrolysis, FaCl3 plus 3H2O, the double arrow, FaOH3 plus 3HCl. For thermal decomposition, we have PCl, the double arrow, PCl3 plus Cl2. For esterification, we have CH3COOH plus C2H5OH, then double arrow, CH3COOC2H5 plus H2O, and the last one is the evaporation of water in a closed vessel. H2O, then double arrow H2O. Next, chemical equilibria. It is a state where the reaction reaches a point after which no further changes occur in the amount of this species. Example is salt dissolved in water. As you add salt in water, it dissolves. But as you continue to add more and more salt in the water, and the water is not capable of dissolving the salt, it is where it reaches its equilibrium. Next, we have thermodynamics and equilibrium chemistry. So what is thermodynamics? Thermodynamics is the study of thermal, electrical, chemical, and mechanical forms of energy. The study of thermodynamics crosses many disciplines, including physics, engineering, and chemistry. Of the various branches of thermodynamics, the most important to chemistry is the study of the changes in energy occurring during a chemical reaction. Consider the equilibrium reaction involving solutes A, B, C, and D with stoichiometric coefficients A, B, C, D. So we have here AE plus BB, then double arrow CC plus DD. So the AE plus BB is the reactants, while the CC and the DD are the product. Based on the insight of Berthollet, the reaction may move to left, to right, or in the state of equilibrium. chemical systems spontaneously react in a fashion that lowers their overall free energy. At a constant temperature and pressure, typical of many benchtop chemical reactions, the free energy of a chemical reaction is given by the Gibbs free energy function. So what is the Gibbs free energy? It is a thermodynamic function for systems at constant temperature and pressure that indicates whether or not a reaction is favorable. If delta G is less than 0, then the reaction is favorable. If delta G is greater than 0, the reaction is unfavorable. If delta G is equals 0, then the reaction is in equilibrium. The equation is given as delta G equals delta H minus T delta S, where delta G is the difference in the Gibbs free energy, delta H is the change in enthalpy, delta S is the change in entropy, and T is temperature in Kelvin. So what is enthalpy? It is a change in enthalpy indicates the heat absorbed or released during a chemical reaction at constant pressure. So if delta H is negative, the reaction is exothermic. If delta H is positive, the reaction is endothermic. So entropy. It is a measure of randomness or disorder. The entropy of an individual species is always positive and tends to be larger for gases than for solids and for more complex rather than simpler molecules. Reactions that result in a large number of simple gaseous products usually have a positive delta S. Flashed on the screen are examples using the equation of Gibbs free energy. Using this same example and to better understand this, let's have this. Let's have the first example. Calculate the Gibbs free energy change or delta G for the following chemical reaction. First, we have ATP yields ADP plus pi. The reaction occurs at 68 degrees Fahrenheit. The change of heat or delta H is equals to 19,070 cal and the change in entropy or delta S is 90 cal over K. So for the solution first, since the given is in Fahrenheit, we have to convert it in Kelvin. So we cannot directly convert Fahrenheit to Kelvin, so let's have it converted first in terms of Celsius. So degree Celsius is equals to degree Fahrenheit minus 32 times 5 over 9. So we have 68 degree Fahrenheit minus 32 times 5 over 9 is equals to 20 degrees Celsius. So let's convert this in terms of Kelvin. Degree Celsius plus 273. So 20 plus 273 is equals to 293 Kelvin. So moving on to the equation, we have delta G is equals to delta H minus T times delta S. So we have the delta H, which is in the given 19,070 minus the temperature, the 293 Kelvin, and the delta S, which is also in the given, which is 90 cal. So solving it, we have negative 7,300 cal, or convert it in terms of kcal, we have 7.3 kcal. Let's have another example. Let's have the reaction glutamate plus NH3 yields glutamine plus H2O. The reaction occurs at 68 degrees Fahrenheit. The change in heat or delta H is equals to 4,103 cal, and the change in entropy or delta S is equals to 2.4 cal over K. So solution, since we all know that 68 degrees Fahrenheit is equals to 293 Kelvin, let's directly substitute the formula. Delta G is equals to delta H minus T delta S. So delta H is equals to 4,103 minus the temperature 293 times the delta S, which is 2.4 cal over K. So we have 3,399.8 cal, or convert to kcal, we have 3.4 kcal. In some instances where a system moves from a non-equilibrium to equilibrium position, delta G must change from its initial wave to zero. The equation is given as delta G equals delta GO plus RT and Q, where delta G is the free energy at the moment, delta G with the exponent of 0 is the standard state free energy, R is the ideal gas constant which is 8.314 joule over mole K, T is the absolute temperature in terms of Kelvin, and Q is the natural logarithm of the reaction quotient. So Q is equals to C raised to the power of C, D to the power of D over A to the power of A, B to the power of B. The terms in brackets are the molar concentration of solutes. The concentration of the products are placed in the numerator and the concentration of the reactants in the denominator. Each is raised to a power equal to its stoichiometric coefficient in the balanced chemical reaction. Flashed on your screen is an example. So to better understand this, let's have this. Using the same example, consider the reaction 2 is O2 plus O2, the double arrow 2SO3. So calculate the delta G of the forward reaction when the concentrations of SO2, O2, and SO3 are 0.100 m, 0.200 m, and 0.950 m at 1455 K. We also have R, which is equals to 8.31 J over mole K, and the delta G to the power of 0 equals negative 142 kJ over mole. So for the solution, we all know that Q is equals to CC DD over AA times BB. So we only have one product, so we have SO3. So we have 2 moles of SO3, so the exponent is 2 over 2 moles of SO2, so SO2, and 1 mole of O2, so it is understood that it has an exponent of 1. So to solve, we have the concentration of SO3, which is 0.950 to the power of 2, the concentration of SO2 0.100 to the power of 2, and the concentration of O2 0.200. So we obtain the result of 451.25. To substitute in the formula, we have delta G to the power of 0 equals negative 142 kg over mole plus R, which is 8.31 J over mole K, and temperature is 1455 K, and the Q, which is 451.25. So to solve, we have negative 142 kg over mole plus 73,900 joule over mole. So since we have here the kg, we will convert this into kg. So we will have 73.9 kg over mole. The final answer is negative 68.1 kg over mole. Lastly, when delta G is equals to 0 or at equilibrium, the equation is given as delta G to the power of not equal to 0 equals negative RT and K. So they rewrite the formula. So we have NK is equals to negative delta G to the power of not equal to 0 over RT, and they come up with the final formula, which is K is equals to E to the power of negative delta G over RT. So we have here an example. To better understand this, let's have this. Using the same example, calculate the value of K at 298 K for the following reaction, given that delta G is equals to negative 32.96 kg mole to the power of negative 1. So the reaction is N2 plus 3H2, then the double arrow, 2 and H3. So in key is equals to delta G to the power of not equal to 0 over RT. So substitute, we have here 30,960 over R, which is the 8.31, temperature, which is 298K, is equals to 13.3. So using the final formula, we have e to the power of 13.3. So the answer is 5.97 times 10 to the power of 5. That is the value of key. You might be wondering how to solve A, so this is how you solve this. Grab your calculators. So first, press the alpha in your calculator. Then look for E. So this is E. Press. So it will show it here. So we have now E. Then press the exponent. So using this 13.3, so I will type 13.3. So we have now the answer 597,195.6138, or the same with 5.97 times 10 to the power of 5. That would be all, and I hope you learned something. Thank you.